Hello, my name is Darren Thomas and I am the Director of Educational Research Techniques. This is Easier, Practical Applications of Machine Learning Algorithms in R. We're now in Unit 6, Lesson 3. And what we're going to do now is that we're going to use four different, it's all going to be support vector machine. Let me slow down. We're going to use the support vector machine algorithm for predicting income for the data that we prepared in the prior lesson. However, what's going to be unique is that we're going to use four different kernels and we're going to compare the results of each kernel. So having said that, let's go ahead and move over to RStudio. So you can see here I'm inside RStudio, and now we're going to use four kernels. So in line 1, we're going to use a linear kernel, then we're going to assess it. Then in line 15, we're going to move over to the polynomial kernel. In line 29, we're going to use the radial kernel. And then lastly, in line 43, we're going to use the sigmoid kernel. So we're using these four different kernels, and we're going to compare the performance of each one. However, it gets even more complicated than that. We're also going to be tuning the different kernels. In other words, we're going to have to set the different hyperparameters to different values and see which value performs the best. This is very, very common when you get into more advanced styles of machine learning data science, in that you don't just settle for the default hyperparameter. In other words, that default value for whatever it is. And what I mean by hyperparameter is this is a parameter that you have to set a value for in order for the model for the algorithm to function. In other words, the computer or the algorithm cannot determine the appropriate value for this particular hyperparameter in order for it to converge and to analyze the data, if you will. And so we're going to go through this piece by piece, step by step, and then we're just going to go through the whole process here. Now, I also need to mention that don't forget that you need these libraries here from the code in 6-2 in order to be successful. Some people, they do the whole unit all at once, so they don't have to keep reloading these packages. Some of us, we come back and forth, and so if you've left RStudio since the last time you've been inside it, you have to reload these packages. So having said that, here we are in Unit 6, Lesson 3 again, and we are going to start by running this linear.tune. So the linear kernel just draws a line. It's linear. And the hyperparameter you have to set is called the cost function here. Again, the details behind how this works is kind of beyond the scope of these videos, but we've set it here to some general values. We don't know what value is the best, but we're just setting it to these. And you have to do this in order for the algorithm to work. And so the function that we're using here is the tune.svm. It comes from the E1071 package. And so I already ran these before the video because sometimes they take a little bit of time in terms of computational power. And so now in line 3, we're just going to press Control Enter, and you can see right there the results. And so here you can see that it's a tenfold cross-validation. We'll talk about that later towards the end of the video series here. And then it shows you the different values. Now here, if you look closely, you can see that we have 6 different models here. In other words, these are the 6 different values that we set our cost function to. That's why we have 6. And the RStudio tells you which setting for the cost function gave the best performance. So in this particular example, when we set it to 10, which is the last one, you can see 1, 2, 3, 4, 5, and 6 here. When we set it to 10, we got our best performance. All right, so that's the one we're going to use right here. So in line 5, what we're doing now here is that we're creating an object called best.linear. This is our best linear kernel performing model, and we're doing that by doing linear $best model. And so it's taking the characteristics of the best model, which again is line number 6 right here down below in the lower left hand corner, is taking the characteristics of that model, and we're using that to predict our data. That's what we're going to do. So here's what's happening in line 6. We're taking our best model, which we call best linear, we're using the test set, and we're saving all this in an object called test.tune. And so I've already done that. And so now in line 7, we can make a plot where we compare our predicted values to the ground truth of the test set. So go ahead and take a look at that. And you can see that's a pretty darn straight line there. It looks like we have a very good strong correlation between what was predicted and what actually is the truth here. And so it looks like our model is performing very well. Now we can confirm that by doing some additional things. So first off, I need to get the residuals. that is the difference between the actual values in the test set and the predicted values. So in line number 9, this is what I'm doing here. I make an object called tune.test.recid, and inside that object, I'm subtracting the tune.test, the results from that, the predictions of our model we created, and I'm subtracting that from the actual values of the test income. So after I do that, I can now look at the square, the mean square values of this. And this is just one way to do this. So I square the residuals, that way I remove the influence of the negatives, everything is positive, by squaring them, and then I calculate the mean for that. And so you can see the average error, if you will, is 0.21. And then after that, of course, I can calculate the correlation between what's happening here between the tune.test prediction and the actual test income values. And you can see that there's 0.85. So very close to 1. And lastly, I can look at the summary statistics of the actual predictions. And all this is for comparison. Right now, it's hard to appreciate this, but when you make several different models, you can compare their performances by looking at the mean squared error, by looking at the correlation, and by looking at the summary statistics. And so by doing this, you can have an idea of how well our model is doing here, if you want to know that. All right? So let's move on now. Now in lines 14 and all the way down here to about line 27, we are going to use what is called a polynomial kernel. So this is useful for when you don't think that your model, that the data is following a straight line. So again, I already ran this prior to the video. I'll show you the results in a second, but there's something else I need to talk about. You can see here that now we have two hyperparameters that we have to set values to. So we got degree here, so the degree of the polynomial, third degree, fourth degree, fifth degree, and the coefficient theta. Again, another value that you have to set. So I have 3 here, and I have 1, 2, 3, 4, 5, and 6 here. So altogether I'll have 18 different models, because 6 times 3 is 18. That's what's going to happen. And so all these are ran at a time or whatever, and then we get the results in line 18. So you can see here, like I just told you, there are 18 models, like I just told you. And the best performing one had an error of 0.43. So it's like about all of them. So I can already tell you that this is probably not the best kernel for this situation, because all the values are the same, no matter what degree, no matter what coefficient. Now, all this information right here in lines 19 to 21, we've already talked about this. But now, instead of it being a linear.tune model, it's now a poly.test model is what we're doing here. So first we take the best model in line 19, then we do predictions, and then we plot. So let me show you the plot. And you can see, it's a little bit different, not as clean as the last one, but not bad. And so of course in line 23, we calculate the residuals, and then line 24, here's the average, 0.27. The correlation is 0.80, which is pretty close to what we had before. And you can see that we have our summary statistics right here. And so you would compare these to the actual statistics for the actual, the actual results of the ground truth, if you will. So next we're doing a radial kernel, and this one has the hyperparameter of gamma. And so I have my 6 values there. In line 32, let me show you the results. So you can see here that we have 6 models, because remember, we have 6 values inside our hyperparameter, and the best one was 0.53. So it looks like when the gamma set to 0.1, this guy right here. Now, what we're going to do now is we're going to, of course, you find the best model in line 33, and then you predict in line 34. Remember, I did that before the video so that you don't have to wait for the computational time. And now when we plot, you can see right here, it's a little bit more spread out. Again, you can see the last one. You can see not quite as well, not doing as well. All right. In line 38, in line 37, we calculate the residuals. Here's the mean for that. In line 38, you can see it's 0.32. Not a whole lot to brag about there. It's not performing as well as the other models, but we'll talk about that more in a second. The correlation has gone down, and here are the summary statistics. Now, here's our last one, the sigmoid. Again, I can already tell you this is not going to work, but we're just having fun here. Sigmoid is really, really good for like a classification primarily. But you can see here that it has 2 hyperparameters, gamma and the coefficient theta. So let's see here. I have 1, 2, 3, 4, 5, 6 here. 1, 2, 3, 4, 5, 6. So I should have 36 models altogether. And again, you have to play with appropriate values. I don't have any guidance on how to do that. In line 46, we now have the summary for that. And you can see, like I said, 36 models. And the best performing one had a value, an error of 1.00. And that is found right here in model 31 here. When, let's see here, the gamma is set to 0.1 and the coefficient is set to 4.0. All right, so we're doing really, really well here. Now, of course, in line 47, just like I've done 3 times before, I have to take the best model for my sigmoid.tune object. And so I've done that already, and then I predict, and now I can plot. And you can see this is pretty messy. This is not going to work, and again, that's not surprising because this kernel is not appropriate for this type of data. Line 51, of course, I go again through the process of finding the residuals here. In line 52, I square them and add them up and get the mean. So you can see 0.68. This is much higher than the other ones. The correlation is much lower at 0.54, and here are the summary statistics. So looks like we're just about done here. Now, one thing I would like to do is summary. Let's see here. Test dot. Let's see, income. That's what I want. All right. So what we're going to do now is, I'm going to take this. I need this. And we're going to move over, and I'm going to show you kind of a summary of all the things that we've done so far. So here we go. Let me paste this in here for you. All right. So what we're going to do now is we're going to compare the performance of the different models. So I just put them all in a nice little spreadsheet here so we can see them all at once. So here's what's happening. So you can see here are the results for the linear and also for the polynomial. So you can see that for the mean error here is the lowest for the linear model. So 0.21, then for radial is 0.32, for sigmoid is 0.68, and then for polynomial is 0.27. So in terms of the lowest amount of error, linear is superior. And also you can see here for the correlation, linear is also superior. 0.85, the polynomial got 0.80, radial got 0.76, and the sigmoid got 0.54. Now, so again, linear is the boss here. Linear is the best performing model. Lastly, we have the summary statistics. And now to understand this, you have to compare it to the ground truth, which is for us down here. So let me see if I can move that closer. Oh, it took everything. Okay, so here we go. So here we got 1.58. Hold on, I can do this a little bit better for you. We got 1.58, all these different values here. Oh. All right, so you can see right here that we got 1.58 negative here on the test, but then we got 1.61. That might be a negative. Maybe I left off the negative number there. Okay, yeah, this should be up here. Okay, and so again over here we got for the polynomial we got negative 1.38. So it's very good at predicting that first value. Then you can see here, so you can compare. You can compare the summary results of the different models with the actual ground truth, and they should be similar to each other. They should be equivalent. So you can see for like the sigmoid value, the max is 0.32, while the max down here is 3.68. That's a huge difference. And then we had all negative numbers going across here, whereas at the third quartile, there's a big difference there. So you can see how there's differences. Now, if you look over here at the linear model, you can see 3.85, 3.68. We have some problem with the third quartile, 0.21 with 0.47. The means are reasonably close, somewhat. And then after that, it goes on from there. The medians are very close, the quartile. So again, you can see that the linear model is giving the best approximation of the actual truth of the data. And that's the power of using these different metrics to see how your model performed. So let me go back and try to explain what we've done here, and then I will conclude the video. So in this video, what we did was very simple. We developed several different support vector machine models that all use different kernels, and the kernels are just ways of transforming features for whatever our purposes was. Now, when you're dealing with support vector machines, you have to keep in mind something called hyperparameters. These are parameters or statistics that cannot be estimated by the algorithm or by RStudio, and you must put in some sort of a manual value, or it will use a default value. The beauty of the tune.svm function is that you can put in several different values, and it'll calculate, it'll run, develop models for all these different hyperparameters, and then it will help you define which one did have the best performance. Once we did that, we just looked at the summary, and then we took the best model. We did this 4 times. We then predicted what the best model, and then we plotted it to see a visual. And what I mean by plot is that we took the predicted values and compared them to the actual values. And the closer the values are to 1, the better the model was at performing. Then, of course, we dealt with the residuals. We calculate the mean for the residuals. The lower the number, the better. And we calculate the correlation. Of course, the closer to 1, the better. I already talked about that. And we took the summary statistics for the predicted values. And this is useful not so much to compare model to model, but rather to compare your model to the actual summary statistics of the ground truth, which comes from your test set in this particular example. So I hope that this video was useful and you were able to understand what we were talking about and how things work in this particular experience with support vector machines. My name is Derek Thomas. I am the Director of Educational Research Techniques, and this is Easier, Practical Applications of Machine Learning Algorithms in R. Take care.